So many of you attended the tutorial this morning, and you've been hearing about differential privacy for 10 years now. And so you might say, sort of, why aren't we done? And despite the fact that there are a lot of tools and a lot of things, complicated things built up from simple things, we can think that we're sort of in an analogy to the state of the art of numerical analysis in the 1970s. So now, let's say you want to compute some sort of matrix decomposition, and the first thing you try turns out to be wildly unstable, and you say, oh, right, there's a book on this, and you go to the book, and you find the algorithm that was somebody's PhD thesis in the 1970s. So that's sort of where we are now. We're doing the PhD theses, and there's a lot of work that needs to be done. So I'm going to talk about at least one and maybe two results. And the first work is joint work with Weijie Su, who was doing a PhD thesis at Stanford in statistics, and Li Zhang, my colleague at Microsoft. Now, I'm not going to remind you of the definition of differential privacy unless you need this. So do you all know the definition? It is so nice to give a talk where I don't have to give the definition. So just remember the model that the data analyst, who is also our adversary, asks a question Q1, gets some sort of answer. Based on that, chooses a reply Q2 and gets another answer, and so on and so forth. So that's our model. It's centralized. Now, during his tutorial, Adam mentioned briefly report noisy argmax, or also report noisy max. So let me just briefly remind you, suppose you have a data set X, and you have a collection of functions, G1 up to Gm, and you want to know which of G1 of X, G2 of X, and so on is the largest. Okay? So here is the algorithm to do it. It's very simple. First of all, you compute, but do not release yet anything to the public. Just compute these values. And then you add noise that intuitively is scaled to the, or not intuitively, is actually scaled to the maximum sensitivity. That's how much the function can change as we change the data of just one person. The maximum sensitivity of any of these functions divided by epsilon to have epsilon differential privacy. So you add that, and you report the index of the winner. So you basically compute the true values, you add some noise that's appropriately scaled. One of those is now the largest value. You report the index. You say it is function gi that achieves the maximum. Okay. Don't release any noisy values. That is epsilon differentially private. And the proof of epsilon differential privacy is just a straightforward case analysis. If you also want to get the value of the function, then you have to simply ask for the value of the function computed in a differentially private way. And that will either cost you an additional privacy loss, or you can scale things so that each of these has privacy loss only epsilon over 2, so that cumulatively the privacy loss is epsilon. So you can do that with max, and obviously you can also do that with min. And I want to just remind you that from the composition theorem, the advanced composition theorem that Adam mentioned, if I wanted to play this game k times to get the k approximately smallest functions, gi of x, or largest, then the amount by which I have to increase the noise is not k, but it's something like the square root of 2k, log 1 over delta, if I'm going to achieve epsilon delta differential privacy. So those are the only facts about differential privacy that we're going to be using in the talk. So now I want to talk to you about property testing, because that's what, not property testing, hypothesis testing, because that's what the false discovery problem is all about. So let me introduce you to the null hypothesis. In hypothesis testing, the objective is to determine whether an effect, such as the drug increases life expectancy, or this location in the DNA is correlated with the disease, whether an observed effect is true or not true. Now, why would an observed effect sort of not be true? Well, it may have to do with you being unlucky when you chose your data. that you had a statistical fluke, exactly a statistical fluke. And the data that you chose for this particular hypothesis were not representative of the population as a whole. It's unlikely, but it could happen. Okay. So the goal in hypothesis testing is to, as they say, reject the null hypothesis. The null hypothesis says there is no effect. Nothing interesting is going on. The drug does not affect life expectancy. This location in the DNA is not associated with the disease. So when can you reject the null hypothesis? And the problem, again, is distinguishing random effects, which come from statistical flukes in your sampling, from true effects. So the statisticians introduced a notion of the p-value. The p-value is the likelihood that an observation as extreme or more extreme than the one that you have observed would in fact happen if nothing interesting were going on. Okay, so it's kind of backwards. The likelihood of seeing an effect this extreme or more if in fact nothing interesting is happening. So in some sense, it's the likelihood that you should attribute this to a statistical fluke. And often there's an assumption that the p-values of the null hypothesis should be uniform between 0 and 1. So the computations, the things that compute p-values are set up in a way that the null stuff is uniform, and hopefully the non-null stuff is different than that. Okay, so how small should a p-value be in order for you to decide that something interesting might be going on?
Yeah, are you going to define the p-value?
I am not going to tell you how the p-value is computed. I gave you the property of a p-value, which is what we care about, and I'm going to be using the fact that the p-values of the nulls are often assumed to be statistically no less than uniform. Okay. So the standard threshold is something like 0.05 or 0.01. Now, that's great if you're testing maybe one hypothesis or a couple of hypotheses. But suppose you're testing 1 million hypotheses. Think about these hypothesis tests when you compute the p-values as taking balls and throwing them at uniformly at the interval 0, 1. If you use a threshold of 0.01 and you test 1 million hypotheses, you expect to find 10,000 true nulls below 0.01. You're not getting any information. This is not good. And especially as people get into DNA testing, you know, the genome-wide association studies, where they truly are testing 1 million hypotheses, 1 million locations in the DNA, these numbers are serious. So one alternative is to be very severe and divide your threshold by m, the total number of tests. But there's another approach that is very prominent now in the statistics literature. So they ran into a brick wall and they said, okay, let's change our goal a little bit. Instead of saying, let's try to be sure that we never say something is interesting when it's truly not interesting, let's instead change the goal. And let's say, okay, fine. Let's change the fraction of things that we reject. Let's control the fraction of nonsense in the total number of conclusions we draw. Now, I have to say that a very confusing thing from the statistics literature is that the stuff that we would call accept, they call reject. They are rejecting the null hypotheses, saying something interesting is happening. So it's very confusing, and if you ever forget what reject means, ask me. But I'm going to probably stick with their language. Okay, so instead of trying to make sure you don't reject any true nulls, you want to control the fraction of true nulls among the things that you reject. And so they define the false discovery rate, which is an expectation of basically the ratio of true nulls, nonsense, divided by the total number of things that they reject. And they want that ratio to be small. So that says that you might accept 100 things, but if you have controlled the false discovery rate at, let's say, 1/3, then at most 100 over 3 of those should be nonsense, and the remaining 2/3 should be good. Yes?
Are you trying to make a minimum guarantee on the number of, oh man, I go wrong with the rejection here. The number of...
You can say good stuff and bad stuff if you want.
The number of true positives that you fail to find, right? So you fail to reject something that you should reject.
No, this is only the other direction. Right. What you're talking about is power, and this is false discovery control.
But you're not going to this talk. You're not going to
No, I'm going to sort of appeal to some authorities on this, and yeah. Okay. Now, I have an expectation there. But the algorithm is going to be a deterministic algorithm. So the expectation is over the sampling that created the data set. All right? So again, if there's ever an expectation and you're not sure which it is, ask me. I try to keep it restricted to the data set here. All right. Great. So here's an algorithm that, so the idea of controlling the false discovery rate is due to Beniamini and Hochberg, and here's an algorithm that's commonly referred to as BHQ, where their goal is to control the false discovery rate at Q. So Q is it's a ratio, it's just a number between 0 and 1, and the p-values are the p-values for the m different hypotheses, and when you see the parentheses in the subscript, that indicates that I'm talking about sorted values. So p parenthesis 1 parenthesis is the smallest. P parenthesis 2 parenthesis is the next smallest, just as the picture shows. All right, so they defined some thresholds, and the thresholds have the form j over m, where j is going to range from 1 to m, times q. Q, again, is the rate at which they want to control the false discovery. At most, a q fraction should be nonsense. Now, here's their algorithm. They start at the right-hand side with j equal to m, and they say, is this p-value less than the jth threshold, less than the mth threshold? If so, they say, we're taking everything. And otherwise, they say, OK, forget that. We'll go down to m minus 1. And so they iterate until they find a j such that the jth smallest is less than the threshold alpha j, and then they take everything to the left. So the algorithm is clear? Now, the proof of this is astonishingly subtle, but here's a little bit of intuition. Suppose all of your hypotheses are really null. Everything is crap. Now, remember, the p-values of null things are uniformly drawn between 0 and 1. So in the interval that is 0 to the jth threshold, remember we're throwing m things in there, we'll multiply this by m and we'll see that we should get jq p-values in there if they were all null. But q is less than 1, and this is the jth smallest. So that means there are j down here. Not j times q, which is tiny, but j, which is substantial. And so you've got too much stuff, intuitively, for it all to be lousy. So intuitively, at most, a q fraction of that stuff will be true nulls, and the rest is going to be good stuff. So that's the intuition behind the algorithm. Now, suppose we tried to make this algorithm private. That is, we want to carry out this algorithm in a differentially private way. I should mention, by the way, that there is a very vast literature on controlling the false discovery rate, and on the BHQ method in particular, and various descendants of that method. So, suppose you wanted to do this in a differentially private way. Well, the first thing that you could try is to do kind of exactly what you did before, only you can't really look at the p-values because there are lots and lots and lots of them, and to see all of them in a differentially private way would turn out to be, you would have too much noise. You wouldn't get any meaningful signal. But, yeah. Adjacent data sets are data sets that differ in the data of just one person. So all of the p-values could change if I change the data of just one person. Some could go up, some could go down, they could all change. So changing one person changes all of these things, so it's a very sensitive calculation. Thanks. Okay, so remember the original algorithm is look at the largest p-value and see if it is less than the largest threshold. If so, take everything, and otherwise go down to the next one. So I could ask for the largest value in a differentially private way, and I'll get approximately the largest value using report noisy max. If I happen to luck out and everything is less than the threshold, then in some sense, everything is great. There's a slight bit of slop having to do with the noise, which we have to address, but we'll get more detailed in a minute. But if it turned out that the noisy largest p-value was not less than threshold, then I would have sort of paid a privacy price because I had done a computation here. I have gotten nothing for my efforts, and I have to continue. And remember, I'm worried that m is very, very large. So instead, we're going to start with the smallest one, not report noisy max, but report noisy min. And we're going to look and see, give me an approximation to the smallest one, an approximately smallest one. If that's less than the smallest threshold, I will reject that, that's good stuff, and I'll continue, and now I'll go on to the second threshold. And we'll continue like that. So this turns out in the non-private world to be a very well-studied variant, and the claim is that it seems to be in practice as powerful. That is, it finds as much interesting stuff as the original one that started from the right. To make things really confusing, the statisticians call this the step down procedure. I would call it step up, but they call it step down. But nonetheless, when I talk about non-private BH for the rest of this talk, I mean starting at the left. Now, so first of all, it has good roots because it's well studied and appreciated in the literature. We'll proceed, and every time we sort of pay, we found either we were done or we found something else useful, and we continue. So that's nice. And now I'm doing something that Bignamini and Hochberg did, although not as interesting. What they did was amazing. And I'm going to say, let's change the problem one more time. And I'm going to not do this until I fail, but I'm going to stop at some point, some predetermined point, say after K trials, after I've gotten K things. Now, that's obviously weaker. But is it reasonable? Well, here's the argument for why it's reasonable. One of the reasons for trying to find, for carrying out the multiple hypothesis testing is to find directions for future and deeper research. And you don't have the resources necessarily to carry out 1 million subsequent studies. You might have the resource to carry out 10 or 100, maybe. But it's reasonable to think in terms of K being bounded. If I find K things of which a 1 minus Q fraction are good, then my follow-up studies could still be useful. So we're going to stop at some K, and K is going to be a parameter in the algorithm. So again, when I talk about the non-private version, I mean starting at the left and comparing to thresholds and rejecting until we fail. So here's the outline for the rest of the talk. First of all, I'm going to highlight some properties of the non-private algorithm. It's the old non-private algorithm, but these properties that we're going to show that it has are new. That is, it was not shown before. Then we'll have a somewhat detailed discussion of the private algorithm, including how do we compute the p-values in a way that doesn't compromise privacy. And also, we will prove sort of the qualities of our non-private algorithm by reduction to the private algorithm. We will relate the properties of the non-private algorithm, of the private algorithm to the non-private one. And finally, I want to tell you something about the proof of the discovery control, false discovery control properties of the non-private algorithm because it's an interesting addition to that very big literature. Okay, so new properties of the non-private algorithm. So I told you that the p-values are thrown sort of uniformly between 0 and 1. That was the intuition. So that is an assumption that's made everywhere, and also that they are independent. That is going to be the only assumption that we will be making. So in other words, the p-values of the true nulls, the nonsense, are going to be independent and uniformly thrown. But the p-values of the good stuff can be functions of those bad things. So for example, the p-values of the good stuff, the false nulls, could be, say, 1 minus the median of the p-values of the true nulls. Okay. Another thing, another property that's going to be important is the following. Our algorithms will have, the BH algorithms have the property that the algorithm rejects nothing, no rejections, or all of the R rejections, if it rejects some R of them, will be less than the Rth threshold. Okay? Now, that is...
This is the algorithm that goes up or the algorithm that goes
Both of them have this property, and this is going to be the only property that we will be using in our proof of the good behavior of the non-private algorithm.
What exactly are you assuming about independence? That where which values are independent?
The pink, sorry, you haven't seen the color code yet. The non-null, the true nulls, the nonsense stuff, are independent and uniformly chosen.
Pairwise or completely?
Completely. Okay. Jointly independent. No, probably not. And I will venture to guess that it's close to approximately true, and that this is why the statisticians live with it. Okay? And since everything we're going to do is going to be a reduction to what they do, I'm not worried about it. Okay, so the theorem that we prove for the non-private algorithm is the following. If you assume this independence property, and you ensure that the algorithm satisfies this compliance property, where the alpha j, the threshold alpha j is j over m times q, it's the one you saw before, then for a fixed constant, the false discovery rate is bounded by this, and a slightly different false discovery rate, which is what we'll spend all of our time on, is bounded by c times q for this fixed constant c. So this rate, this is an expectation where you get value 0 if there are fewer than 2 nonsense discoveries. So in some sense, you don't charge if the algorithm only finds 1 false discovery. You don't look at the ratio. You wait till you get to 2 false discoveries. Okay, now just for comparison, this is the only thing we need from the algorithm. So that means that there can be gaps. You saw in the non-private version that we rejected everything to the left of the point that we had in mind. We're going to allow some gaps. That is, we're going to have a different proof that permits some gaps. And just to compare, we're controlling at the rate of c times q, where c is a constant less than 3. The original Beniamini-Hochberg was controlling at q, but it assumed that the true nulls were also independent of the false nulls. So they were making stronger independence assumptions. And if you completely get rid of all independence assumptions, the Beniamini and Yacutelli work gets again control at q, but they're paying with the thresholds. They're being much, much more stringent by a log m factor in terms of what they can take. So they'll get lower power. Okay. So here's the private algorithm. P-values are computed by algorithms that operate on data sets. And you've seen mostly, I guess, in the tutorial, additive noise that depends on the sensitivity of the function. When the p-values can be very, very small, the additive noise can be terribly nasty. So instead, we carefully work with the logarithms of the p-values. But we need to be careful. So we define an odd notion of eta nu multiplicity. Basically, it says that the computation is eta nu multiplicatively sensitive if for all adjacent data sets x and y, either both of them have p-values less than nu, or there's this nice multiplicative relationship between p of x and p of y, which is e to the eta. That means when we take the logs, the difference will be an eta plus or minus eta. Okay, so it's a multiplicative sensitivity gives an additive sensitivity in the logs, but we're sort of deliberately not dealing with things that are too small.
So what kind of tests do these things go through?
So I will talk about that briefly at the end, but a lot. Okay? So once you have this, you can use the Laplace mechanism on the logarithm scaled to eta over epsilon, but you have to be careful about the things that are really too small. And you'll see very quickly how we do that. You asked p-value computations for nice multiplicative sensitivities, and you'll see later what I mean by nice, are a very, very rich class. Okay, so here's the private algorithm. We have our threshold Q. We have the eta and nu from the definition of sensitivity. We have the number of functions, hypotheses m. We have k, which is our stopping point, and epsilon and delta. And we have a collection of thresholds. And we have algorithms for computing p-values. So first of all, to deal with the fact that some of the p-values are small, we replace p of x by phi of x, where phi is just the max of our lower bound and p of x. So we push some things arbitrarily higher. And then we take the logs, because remember, we're going to be playing with the logs. And so if you've noticed down here, these are our phi values. Some of these guys had gotten moved up arbitrarily to nu. Then we take the logs, and true, the scaling changes, which I didn't draw, but the ordering didn't change. Okay. And now here's the algorithm. You run report noisy min k times to peel off the k approximately smallest p-values and their approximate values. Those approximate values are called y1 up to yk. The y1 is taken the first time, y2 the second time. They may be out of order. y2 could be smaller than y1, and so on. These are sort of pseudo p-values. Now run the Beniamini-Hochberg algorithm, the one that I described, starting from the left and moving up, on those noisy values with the thresholds that are given. That's the algorithm. Okay? So basically, you take care of the small values, you take logs, and now you run Beniamini-Hochberg on the approximate logs. So notice that, let's say in this picture, these are the logs, and I add some noise, and the ordering could change. This guy moves right, this guy moves left, these guys swap places. So in general, the jth smallest noisy logs will not necessarily be the noisy versions of the jth smallest log of the true p-values. We don't care. Okay, so here again is our algorithm. Why is it private? Well, when we use report noisy min, we'll just use the we'll just use the amplitude for the noise that is given from the Laplace mechanism under composition, k-fold composition. So that's it for privacy. We don't have to think about privacy. Now, I couldn't resist. It's right near here. Here's an accuracy lemma. It says that under certain conditions having to do with beta, which is going to be a probability of failure, k is our k that we're interested in, m is the total number of things, and gamma. If we have m times k draws which is what we'll have in the worst case when we iterate on our algorithm, from the Laplace mechanism, then simultaneously all of the noises are bounded by this quantity. Simultaneously. So that's going to be our high probability case. Everything I'm going to say from now on is going to be conditioned on all of these noise magnitudes being bounded by this quantity. This, from here to here, this is B. That's the parameter for our Laplace. I'm going to call this, though, slack, eta times slack. So all of our noise values will be less than eta times slack. Now, corollary, just to remind you, the xi's are the logs of the phi values, and the phi is the max of nu and p of x. So a very simple corollary is we do some draws. We added noise to some of these guys and got some outputs from report noisy min, and we sorted them. But for the jth largest, when we have sorted them, I can sort of say J star was the guy who gave rise to that, the guy that when we added noise gave us this value. So what this says is that your starting point and your noisy ending point aren't very far apart. They're bounded by eta times the slack, and that's immediate from here. All right. So how do we prove power? We argue that, so remember, the way we did this is, sorry. We argue that if the original algorithm would have rejected some number k prime of hypotheses, then so will, I'm sorry, reject means that declared as possibly interesting, right? Then so will the new one. Okay? Yes, I know. Ah, maybe this is how we should look at program committees. Okay. Okay, then so will the private one. And when I say with probability 1 minus beta, what I mean is in the high probability case when all of the draws from the Laplace mechanism are bounded by eta times slack. So the argument is simply going to be that if there are some p values on the raw data without privacy that are less than alpha j, which is what would happen in the original algorithm, then there will at least be j of the y's that are below our new threshold, alpha j prime. And our new threshold is defined here. So the slack, you know where it comes from. And this is coming from the fact that we took phi to be the max of eta and p of x. And then we took logs. So this is what the computation looks like. The only really interesting part here is the following. This is the true jth smallest, largest, I don't know. Counting from the left, it is the jth in sorted order of the log of the phi values. And we add eta times slack to that. So yj, after sorting, is going to be bounded by this, because yj minus the guy that gave rise to it is at most that. And because it's the jth one, there are j minus 1 others to its left. So if xij plus this Laplace value is bounded by this, then xii plus its own Laplace, whatever it is bounded by that same quantity. This is the maximum I might add to xij. So xii starts to its left. If I add its maximum, it too is bounded by this. Okay. So what that says is that we have yj.
Yeah, but that would not be true.
I'm sorry?
You've added a larger maximum to a smaller value than
That is,
After sorting, right?
this is after sorting. And you're absolutely right. And in fact, that's the next point. I mean, after QED power. These might not be the ones that came from those guys, because somebody could have jumped in. But if so, it jumped in sort of below xij plus its maximum possible noise, so its value is less than xij plus the maximum possible noise. And it might not be the same ones. It is absolutely right. Yeah?
Can you remind us what the beta
Yeah.
Or is it like depend on n?
Well, you'll want to pick it to satisfy these equations, and you'll want to pick it to be little. You can pick it to be little o of 1. I'm not sure how small you can go. Okay. Okay. So that shows power. It's very.
Will it be the same hypotheses?
No, that's exactly what this is saying. It's not necessarily the same hypotheses. So we still need to argue. Okay, so we got stuff. That's great. We still need to argue that we have control of the false discovery rate. That's your question, essentially. I told you, yeah, right, great. So how do we argue that? First of all, thank you. This is the theorem that we're going to prove for the non-private algorithm. I showed that to you before. Now, this is the theorem that we're going to prove for the private algorithm. And again, this probability means assuming that all of the Laplaces are less than eta times the slack in magnitude. So remember that being compliant means that when you reject our hypotheses, either you reject nothing or all the rejected p-values are less than alpha sub r. All right? So this says that if you reject j hypotheses, then they'll all be less than alpha j in the, this is alpha j, j times q over m in the non-private version. So just look at the form of the two theorems. Forget what it's actually saying. We're going to show that the private BH algorithm is compliant with these thresholds q prime. So we're just going to take this q and replace it by q prime, and we're going to have the same theorem, but with q prime. Okay. What do I want to say about this? It's one slide. All right. So the interesting thing in this slide, what happens? If we ran non-private on the outputs from the report noisy bin, and we reject R, then we have that the jth one that we reject is less than alpha j prime. If we ran non-private, we run non-private on these things with the thresholds alpha j prime. When we reject the jth one, it means that it's less than alpha j prime. So we plug in what we have for that value. And we let J star be the corresponding hypothesis that gave rise to that. And we look at what it was before we added noise. And we know that we're going to be off by, at most, an additive eta slack. So we're going to get a 2 eta slack. And then we use the fact that the psi j's are the log of these guys, and these guys are bigger than those guys, and we get this connection. And when we plug in the value for alpha j, the original alpha j, we have j times q over m. And we added this extra condition that nu is little o of 1 over m. So this term becomes at most 1 plus little o of 1 times jq over m. This is just a manipulation. And that gives us our result about compliance. And because we proved that compliance controls false discovery, we conclude that this controls false discovery. Now, getting back to this question, it's kind of ugly looking q prime, but it has a very specific form. There's an interesting class of p-values, which are the ones associated with what you would get if each of your samples, each of your people under the null value, null hypothesis, I mean, was like a random coin flip that is heads with probability p. And then you look at, for the p-value, you look at the probability that you would observe this under the null hypothesis. And when you do that, you see that the p-values, roughly speaking, are eta nu sensitive, where eta has this property, this value approximately. And the point here is that when n gets large, q prime is going to 1 plus little o of 1 times q. So we're almost back where we started from, which is very much the goal. And this particular class of p-values is very popular. It's used in a lot of genome-wide association studies and so on. All right. So in the last few minutes,
About the previous slide.
yeah.
So does this impose somehow some condition on like, the lower bound on, and I mean like for
Yeah.
for like
Yeah.
I'm taking 1 or something. So
Right.
yeah.
So everything we're going to be doing is going to stay private, but it's going to become meaningful when n is larger.
So is the log n threshold in order to make sure that q prime is non-trivial?
Mhm.
Is that essentially what?
Yeah.
Okay, that's
Yeah. Okay. So now I want to tell you a little bit about the proof of the control of the false discovery rate for the non-private algorithm. So the claim that we want to make is that if we are compliant with this set of thresholds, which means if we reject our hypotheses, then all of them have true p-values less than r times q over m, then that's enough to get false discovery rate control at q. So the structure is as follows. First, we're going to define an adversarial game. Our adversary is trying to get a big expected false discovery rate, and we want to show that we're not big, that it's a small false discovery rate. So we're going to define an adversary's game, what its little moves are, and what its payoff is, and describe its optimal strategy. We're going to show that the false discovery rate is bounded by the expectation on the payoff, where the expectation now is over the drawing of the data set. And we'll analyze the expected payoff. So the game is simple. First, the true null p-values, which will be pink in this story, are drawn IID from a distribution that's no smaller than uniform stochastically. So, second, our adversary will choose the p-values for the good stuff. It's a crazy game. The adversary will choose the p-values for the good stuff. That's the blue. And then it will choose a subset, possibly with gaps in them, a subset of hypotheses to reject, and the only condition is that it has to be compliant with the threshold. If it chooses to reject S of them, then the maximum p-value has to be less than S times Q over M. So its payoff is the fraction of true nulls, the fraction of stuff in the set that it rejected that was bad, because it wants to build that up. So first of all, its best guess, its best move, is to make the blue points all 0. Because then it has complete flexibility when it wants to choose its set. It chooses a pink value, and then it pads with as many of these as it wants. It wants to pad with very, very few, because it wants the ratio of pink to blue and pink to be big. So it wants to put in as few blues as possible. And we let it do exactly that. And so we only need to look at the pink points, which are the true nulls. And that's great, because then we can bound the false discovery rate by bounding a random variable that's associated with just these pink points. So, how much time do I have? 5 minutes. Great. What is this slide saying? Well, first of all, let's say it rejects some points, R points, and their p-values are pi1, pi2, up to pir. So some of those will be pink, and some of those will be blue. Now, let's call the pink ones, let's put zeros in their superscript. Okay, so these are the rejected pink points, and they're sorted now. So that means that the largest rejected pink point is at most the largest rejected value, okay? Which is at most Q times R over M, because that's what compliance tells us. So we manipulate this stuff a little bit, And we end up here. So what's this? This is how many pink points we rejected, and this is the total number of points. So this is the proportion of false discoveries in this particular execution. We have this particular data set. So since we have to have at least 2 false discoveries to be counted in FDR2, we're going to define FDP2 to be this term. And so it's looking for the J that maximizes this ratio. And now we take expectations. We take an expectation here and we get we take an expectation here and we get an expectation here. And when we do that, that expectation is by definition the false discovery 2 rate. So in one more manipulation, we use the fact that the null p-values are independent and stochastically at least uniform. And we replace the jth null p-value by the jth uniform order statistic. And now we're looking at properties of order statistics instead of properties of p-values. And the key lemma is given here. So to prove the key lemma, this is what we want to do. We're going to use a representation of uniform order statistics in terms of ratios of sums of exponential, IID exponential random variables. So we make m plus 1 draws. That's going to be our denominator. The numerator for the first one is just the first draw. The sum from, this should say like xi1 plus xi2 over the same denominator would be u2 and so on and so forth. Now, once you have that,
The signs are sorted or are they?
These guys are just draws. They're not sorted. Sorry. These are not the xi's from before. These are just exponent. Sorry.
What distribution of the zeta?
They are IID from an exponential, and since we're dividing, the scale doesn't matter. Okay? Now, the terms in the expectation will yield a backward submartingale. And then, in order to get the max, we're going to give known results for the, we're going to invoke some known results for the max of a backward submartingale. So just to give you some intuition, and this will be my last slide, I guess. Yeah. We want this thing. And all I'm going to try to point out here is that these, I mean, formally we want to prove that it's a backward submartingale, but I'm just going to show you intuitively why the smaller terms are sort of larger than they should be. That is, why this max is going to be off to the left for j close to 2 or 1. Actually, I'm going to insist on it being at least 2. So the reason is we want the max of this expression. So we're going to look at these terms, we invert them. I took j over uj, and I took the expression for it, and I inverted it. This is the backwards submartingale. And if you look at this denominator here, just look at the distribution on Wikipedia. It's skewed left. It is small. So when you invert it, it's large. Wait, did I get that right? Oh, good gosh. It is. So this goes in the right direction. Somebody help me out.
K is the number of terms or something.
Yeah.
So when K is 9, it looks large, so it should be small.
So, no. J, so the point is that j over this is going to be, these guys are smaller. Wait. Oh, good God. Oh, sorry.
It should be peaked around k times.
No, so what happens is, this guy over m is going to stay the same. And this guy is going to go in the correct direction to show that the larger thing will be when j is small. And I'm just going to take that offline. I've checked it a million times. It's true.
How
M is big. M is big, so this guy divided by M is just going to the mean. These guys should be going to something bigger than the mean, and they are. Right, okay, good. All right, so that's it, actually. That's what I wanted to show you about false control of the false discovery rate with differential privacy. There was other stuff, but there's no time. Yeah.